All right, guys. So, okay. So today I'm going to talk about this course note from SIGGRAPH 2012, which I found very enlightening for myself as a graphics student. So I just wanted to share. Please save your questions for the very end because it might get a bit long and some of your questions may be answered. But please do correct me if you feel that I'm talking nonsense, because these are new stuff to me as well. So please correct me if you think it doesn't make sense. All right, so I'm going to talk about the BRDF, which is called Disney BRDF. And by the way, this was developed in Pixar, but for some reason everyone now knows it as Disney BRDF. So I'm going to talk about this. This is from 2012, but it was a published paper thing, and then this is a course note on that. So it's kind of an intermediate level for the kind of introduction for all this shading stuff. But still, I mean, although it seems quite old, but it is very state of the art, at least for this industry level shading models, I guess. So don't think that it's kind of outdated technique that I'm going to share with you. All right, so this is about a new shading model that Disney and Pixar was looking for developing it. And the reason behind it is that they want to have this volley to be rendered. And by that time, they needed they were thinking of having all these metals in a same shot, and all these lights and all the dust and dirt and paint. So it was kind of a time for them to shift to something better. And that was the reason of building this new BRDF. By the way, the difference of BRDF is the reflection, so it doesn't scatter through. But if it's a BSDF, then it's the S is from scattering, so it goes through. So it does include the transmission of light going through. So there are a lot of locations in the wall east. All objects, everything looks dusty, so a lot of layers on top. The existing model would be capable of generating these appearances, but it would be just cumbersome. It would be so expensive, and it's not practical for an animated movie. So then they want the shading to be faster, taking less time, and tools that increase productivity tended to increase cost of shaders as well. And one good thing to know is that all these animation studios consider the lighters to be the bottleneck of the pipeline, because you know that once we have a model, so first of all, the guy who is the model or model the thing in diffuse shading or whatever, and then it passes to the shader. That shader is a dude who's an artist, and they know about the material, that if I want to have a copper or a metal, then how it should look like. So they tweak the parameters of the shading, and that's a whole department of the shading group. And then that passes to lighters. And then for lighters is that I don't care if this is a metal or whatever, I just tweak the lights. So that's the kind of challenge, because sometimes you have something that looks like a metal under very specific circumstance, but sometimes it doesn't. It does look like a diffuse. So that means the shader model wasn't. The shader didn't tweak the parameters properly for that specific material. So that is kind of the challenge in whole graphics, because we want to have these departments to be independent, but in practice they are not. So it goes back and forth quite a lot. So that's this note here says that the shaders are the bottleneck, because they have to fix everything so that when it passes through lidars, it still looks like metal, it still looks like what they want. So changing the parameters is quite hard and challenging. So then they want to have more rays, so that makes the ray tracing to be heavier already, and that requires shading, more points, too much time spent adjusting the parameters. As I said, that's like a boring job as a shader, I would say. And then we have the GPU relighting. So then there are all these layers, and it's good to know, if you don't, if you're not familiar with this, that once we have a material, you can assign shaders as a layers to it. So I think Guyo may have notes on this, but when you're talking about this multi-layer materials, then you are thinking of layers of layers of layers on top of each other, and then you are kind of making the full appearance to look like a metal that has a paint on it, and then the water drops on it. So it does look like these layers. But if you think about it, this makes it super expensive, because finding the light interaction with one layer, with one surface, is already hard enough, let alone adding more layers to it, right? So this shaders that have all these layers on top of each other is quite hard and heavy to deal with. But that's basically the goal of this project here. So the new BRDF is developed by working directly with the people who will use it. And that's also a good thing that I found when I was working at Pixar and DreamWorks. They are always like, the developers are working in the same place as the end users. So you know what they want, and it's way easier to develop something in industry than academia, because I think, to me, here at schools, you can go blindly to the end of something, but then no one can ever use it. So to me, that's what I found, that developers whom are working at industry are more to the point. They still do the same research, they still develop the state-of-the-art techniques, but the criteria is that we want something to be practical, not physically pace, quantum level correct. So that's kind of a intuition that I got from my internships. Anyway, then we have this question that, why don't we use these existing models? I mean, what is the motivation out of this new BRDF? And they said it's because we want the broad range for appearance with few parameters. So the lidars and the artists would just tweak few parameters and they would get what they want, which may not happen when you have layers on top of layers, and each has their own parameters. So it's kind of very hard for an artist, which is not technical person as well, to figure out what to set for the parameters. And then the second point here is easy to control directly or with patterns. And the good thing here, again, I would say the difference between industry and academia is that we want flexibility in the projects that reach to the industry. So that's, I think, the gap. If you have a model that works specifically for something, but for that specific thing is doing really well, then no one would buy it in industry. So you need to have something that is flexible enough to cover more appearances, because suppose you want to make a metal and water and skin. If the lidar, as an artist, wants to learn all these materials explicitly and separately, then you would need to train way more people, way more stuff. So that the goal here is that we want something aggregated, that when you tweak this parameter, you will get a skin out of it for some reason. So it's kind of a bottom line that a industry level model should have. And the last one is ability to cheat. That's also something very interesting that I wanted to point out. Again, you will see that in academia, we want killing papers that are scientifically correct. But in industry, I mean, I'm talking about computer graphics, all right? So it's all about hacking. The whole major is based on hack to me, and that's why I chose it. But then you have this ability to cheat and make some appearance that is not necessarily physically correct, but it looks good, right? So that's kind of that's something that all these animation studios are built on, because because we want animated movies to go beyond the reality, right? So that's kind of an important piece, that you have the tool to make something not necessarily physically based, something that you can make vivid emotion out of it, or something that you can make your effect out of it. And the last one here, it says about this anti-aliasing in the shader, because you may have noticed when you have a very highly detailed ground, and then you go out a bit from the camera, and then you see this aliasing happen, this weird patterns you see, like a Moore effect, then those are something that can be handled with multi-resolution techniques. So they are pointing out here that it's very important to have something to be multi-resolution, because in an animated movies, you don't want to change your material and change your appearance for every camera distance. So it has to have this ability for the multi-resolution and stuff, which is important. And then we have other goals. That is the fewer and easier parameters, as I said. We want more consistency for lighting. By that, we mean that if it's a metal under some specific lighting, it still should look like metal if I put the light somewhere else. So that's, remember that the lighter's job are completely independent from the shader's job. So that's what a developer in the shading has to have in mind, that I want something to be consistent, no matter what lighting it's. And then we have layered shaders are free. So again, I said that instead of having one complicated material that when the light comes from this side and then bounces with itself again, and then so instead of that, we can do all these layers and layers and layers. So I have one diffuse, I have one specular, and one. So that that's kind of with no cost. That's why it's saying it's free. So we are allowed to add all these layers on top. And then we have GPU relighting, more predictive of final frames, whatever. Visual features. First of all, we have a few visual features that you can tell from an appearance. It's the first one, which is very important, is the highlight that you see. It shows up on the objects, right? The highlights go to white at grazing angle. If you try to look down on something, then you will see a kind of a hollow haze. That's because of the grazing angle, and this white color shows up. So these are kind of principles that we want to see from a model. And then we have surface. Surfaces have some specular that says that there's no material with complete diffuse. There would be some highlights. Always there are some specular highlights showing up. Then we have a diffuse, disappear at grazing angle. So it's if you imagine that the light hits and then there is a hemisphere on top, right? So then that hemisphere is not covered entirely for a diffuse. They would be always disappeared at grazing angle. So if you imagine that hemisphere, it's now kind of a bit narrower. And then we want to have the HDR images, so the pixels are not necessarily bounded between 0 to 1. So these are kind of the bottom lines for the model. And one other thing that is very important for the shading models is to be energy conserving, meaning that the light has some energy and that hits the surface, we need to decide what where the energy goes. If it's partially transmitted, partially reflected, what happened to it? So it has to be energy conservation, and for that we have this integral for the light hitting the point, and then that integral has to be 1 or less than 1 in case of absorption. Helps driver consistency. That means that if you have a model that is not energy conserving, then you can get weird artifacts like flyaways or noise or something that doesn't look physically correct. And the second point here, helps drive realistic partitioning of energy and behaviors when designing the model, obviously. So this is the visual effects that we want kind of categorized, and there is only 3 parameters that can separate out all these materials. So in the first row, we have non-metal, and then there are 3 different roughnesses. That's a smooth, moderate, and rough, and that only changing the roughness value. So we can have all these fancy terms, but the lighters as an artist have no clue what are those. So we do want to have something that is user-friendly and it would change as we expect. So this is the roughness value that can make something to look rougher. And then on the second row, we see that there is another term, another parameter for the user, which is the metallicness parameter thing, and that makes the reflective to be as you see like a metal, right? So that's the second parameter. So so now we have roughness and metallic to control these, and the third one is color. So having these 3, we do want to see a wide range of materials to be supported, which is way easier and user-friendly than writing down the rendering equation, and there are tons of parameters, and there are like if you change them independently, then you would get weird appearance. So that's kind of the limitation, that we want those to change dependently, so we don't go too far from a weird appearance. So everything in that range would be reasonable. That's the point. Partition energy. Roughness drives the partitioning of incoming energy. And then there is this Fresnel term that you may have heard, is the amount of energy that is reflected back compared to those that is penetrated through the medium. And that would be tweaked by this Fresnel term. And there is a metallic parameter, and that specular reflectivity at normal incident angle, and then presence of any subsurface diffuse. So that makes it to look like metal, very highly glossy, glossy and specular object. Okay, so we have 3 lobes. Here they ended up having 3 lobes, and then there is the one which is called the specular, which takes care of the broad highlights. And there is another one that called reflection, which is in charge of the sharp highlights. And there is the transmission that we will gonna talk about later. But that's the overview of the model. So we have this specular versus reflection, which I don't see people use it this way. I mean, this is again from 2012, but back then it was kind of common to separate these 2 out, but normally is now the same lobe, and that's what we call reflection now. So the specular is what we said, it's the taking care of the highlights, right? And then this reflection is those sharp highlights. And then we have, we want to kind of blend these two out. So we want part of this and a bit of that. So you can take whatever you want. So this is this Fresnel term, which I said is about the amount of energy that is reflected compared to what is transmitted through. And there is this formula from Schlick approximation that everyone uses. And that basically says, as we get low on the incoming angle, it should be, it should look like, it should look haze, and it goes toward white. And this formula right here is basically saying that that cosine over there to the power of 5 is controlling how much we want the Fresnel term to kind of distribute along that hemisphere. And this is kind of an simple interpolation from when you have a light perpendicular to the surface, and then once you have a light that is at grazing angle. So there is an interpolation between white and a base color and a diffuse color. So that's kind of, as you see here, is kind of, if you put it 0 to theta, then you will get one of those C's. So the C is color, that thing is the perpendicular, and then it's the grazing angle. All right, then we have the highlight robes. So this paper here, Ashiman and Shirley, these are from 2000. I thought that they are outdated, guys, but they are not. It's still useful these days. And basically here they want to show once we have different lobes, how to distribute energy. Because if you have a specular and a reflection and a diffuse, so how to split the energy between these. Suppose the light hit the surface and then part of it goes to diffuse, part of it goes to specular. How to handle it? Otherwise you would make energy. If you make energy, then you will see something glowing. If you have a table, then you would see a part of it that is brighter than your light source, which is not physically correct. So that's a challenge. Here we see that they are doing all this remapping to get, so that S stands for specular and R for reflection, and then we have this Fresnel term and the uppercase F, and then we have that G term. That G is the shadowing term. So the combination of these two, the G and F, would make sure that you have the right attenuation weight for that specular, for that specific lobe. So that G of the first G is for specular, and the second one, the last row, is for the reflection. So then we make sure that the addition of these two would sum up to 1, and energy is preserved. Unless we have absorption, of course. When the light absorbed inside the medium, then we will lose energy. But the bottom line is that we should never generate energy. Then we have, so far we discussed about this roughness that can handle the wide range of appearances already. And then the weight for roughness, so that's the Fresnel term and all the shadowing stuff that comes from it. And then we have highlight, fade, and roughness increase, because if you have a high material that has a high roughness, then it means it's diffuse, because it does scatter the light quite a lot, right? So that is just saying that if you have a very small highlight, something less than 0.1 would be considered as a very glossy object. And this derivation right here just says that we have two terms, the R and the S, and those depends on the color for the grazing angle and the color for the perpendicular view. And then we have the integration over that should be 1 minus R, because this is the amount of energy that is reflected. So then we do want the whole thing to be the remaining part of the energy as whatever is transmitted through. Then we have the subsurface diffuse. So if you think about, again, there is a surface, there is this light, some part of it reflected back as a diffuse lobe, some part of it is reflected back as a specular, and the other reflection, but there are some lights that goes through the material, through the medium, scatters through, because there are a lot of particles inside the medium. So you have this subscattering quite a lot happening, and it's very hard to calculate it by just relying on path tracing, because then you have to consider every intersection and taken into account the attenuation. So it would be quite a lot of computations, which is not practical again. So that's the part that the approximation comes into play. We want to approximate all these subscattering stuff that happens underneath the surface, and then it would eventually come back, right? That's why we capture it in camera. Otherwise, if it was absorbed, then we don't care. It is reflected back from the surface, so that's what the subsurface component does. Then we have an approximation that we can model it as a diffuse, because the light that already penetrated through, then it would be scattered enough that this roughness value, no matter is not valid anymore. It's kind of a very broad hemisphere, if you imagine. So the diffuse, like a Lambertian diffuse light, that would be kind of an approximation for the subscattering. So then here, we discussed this recently about having the Fresnel term to be taken into account the subsurface, because if you have the light penetrated through, and then there are some scattering going on, and then it gets back to the air. So this one is the medium. If you want to take this energy loss into account, and you know the F term, which is the Fresnel term, that one is already the part that the light reflected. Okay, so 1 minus F would be the remaining energy that goes inside the medium. And then you have another term, which is now you're inside the medium. If you do F, it would be a reflection inside the medium, continues. But you have transmitted, you have passed the medium and gets to the air, right? So once you get to the air, there would be another 1 minus F term, and the multiplication of 1 minus F times minus F would be the attenuation of the energy that started from the first point, and then what you get out of and the subscattering, the subsurface, would be 1 minus F times 1 minus F. So then we have multi-bounce diffuse. As I said, when you have materials that have a lot of bounces, then you can think of it as a diffuse material already, and then you can model it with this Lambertian function. And there's this another challenge, that once you have this D of MB, that's the multi-bounce diffuse. So that would pick up the color from the medium, but that would be hard for the artist to distinguish it with the base color. So that's why they just take the same color, although the one that is scattered inside the medium is not the same color as what we have in the surface. But then we get the same color from the user, and then we do some math in the background to make it what we want. But the point is, we don't want to overwhelm the artist, because they would end up having something that doesn't look good. Then we have combining diffuse, because now you have this subsurface lobe, and then we do have again all the specular, the reflection. So we want to combine everything together. So here the R part, which is the one that reflected, is the multi-bounce that part of it goes to the diffuse that goes reflected, and the other one minus R, so that's the amount of energy that we that is transmitted through, then that part is ds, and then we can just write it down. It does look fancy, but doesn't do anything. And these are some examples. With the same model, we can get very wide range of appearances. Okay. Yeah, question?
Sounds good. Okay.
Okay.
If Grace will call for appointment, or we can fix appointment right away.
Oh, I think someone has to inform Gopi to mute himself. All
Perfect.
right.
Thank you.
Then we have the transmission side. So
Monday is a holiday. Okay.
Part of the light is penetrated through, right? So in that part we have. So now we're back. Here we want those three lobes that we've been talking about. We have the diffuse, which takes that subscattering part into account. We have the specular, which takes the highlights into account, and then we have the reflection, which would be the sharp highlights. And then for both, of course, we have one part that is reflected and the rest is transmitted. Additional parameters. First, we want to make sure that the Fresnel term can be adjustable by the artist. So that's the roughness that comes from there. And then we have a tint for specular part. It may not seem physically correct that if you have a highlight, the highlight should be white because the light hits on the surface and then reflected back, nothing happens to it, right? But if a light goes through and then have some scattering with the medium and then picks up the color. So having a specular that is tinted is not physically correct, but that's what we want as a shader writer. Then we want to have some scaling terms because suppose that we want to have more of the reflection and less of the diffuse and more of the specular. So these should be weighted in a way that we don't violate the energy conservation. Then corresponding set for transmission. So the same thing that happens on the reflection side, which is on top of the surface, should happen on the back, on the bottom as well. So here's an example from up that has all these kind of materials in the same shot. And with using the same model, we can generate all range of materials by just tweaking these three parameters of those three lobes. And this is another one, and we see that the reflection and the transmission in the same frame. That's very hard to be handled if you want to use layers on top of layers and layers. And this one, you can see that the glass has some highlights, because then in this way, with whatever model outputs, you can use that as an opacity texture and just use it right away. So it would be, because for the glass, what makes it a glass? When you look at it at grazing angle, then the light cannot transmit through, and it would be bounces back, right? So this is the effect that we can get with this model already for free. Then we have the layering, support many layers, give a plausible result, start simple, layer-based, and that's all about it. So here are some examples. We have on the right, we see a diffuse, bumpy material. On the left, we see this highly reflected kind of metal. And then we want to combine these two, which would fail if we just combine them with based on like an interpolation between them. So we don't want to see that part of the transmission that pops up as a highlight. So those are something that doesn't look physically correct. If I have two materials, if I have a golf ball and then I have some gold liquid spitted on it, then it wouldn't look like this, right? So this is another failed example that if I use the illumination result to be interpolated, so the previous one was the material interpolated and this one is the illumination interpolated, both fails. So then what to do when we want to blend the two materials? So for example, we have a dust that is on top of a copper, and then there is water, and then we have liquor, and then what to do with all these layers if you cannot blend it? And then you have to have this energy conservation into account as well. So then there are also the challenge here is that we have a model that is bumpy. So that's the microfacet model that you may know about, all these normals that are perturbated along. Then we have a shading normal, then we have a geometry normal. So having all these normals into account would violate the energy conservation, because you have a hemisphere that makes up from the geometry, and then you have the hemisphere from the shading model. These two normals are a bit perturbated already, so the hemisphere of the intersection of these two wouldn't be a full hemisphere. That means you're losing energy. So these are something that you have to keep in mind. And then we have the data that has to be light and practical again. So these are the layering results. This looks much better if I have some metallic layer blended to a diffuse layer. This one is a better version if you compare with the old one that I showed from blending using the illumination. So this one is using the blending on illumination. And this is an example that once we have in a shot, we have this dusty metal and Wally, we have transmission, we have paint, we have liquor and everything in the same shot. So this is quite an expensive one. If you think about it, next time you watch an animated movie, you should appreciate these more. This is another one. This one is really cool. If you see all the forks on the left and all the reflections, and then you have plastic, you have metal, and I don't see transmission much here, but you do see some subsurface appearance in the same shot already. So then how do I put a display? Oh, then the developer was just saying that we had this cool model that has already covers a lot range of parameters and appearances, but then it says that one day another shader comes to me and the artist and wanted to have even more flexibility. So the point here is that if you think about what we are developing here at the schools, like in academia, should be practical. Otherwise, there is no point for it. I mean, no one would use it. They would just put it in the cover and in the bookshelves. So these are all the hints that we are getting from industry, that what is needed and what should we direct to. And we should not blindly just follow whatever looks fancy to me. This is an example that we have a metal, and then we have the blue one is the water, I guess, the color. And then there is that white thing that is the liquor. So then we have all these materials as a layer, and then you see still that blue bound picks up the bumpiness from the layer underneath. And so it's so that every layer would take care of light independently, and that would be something that we want. So the layers can be added as many as you want, and they're very low in cost. So it's it's free to use for better appearance. Then we have the layering idea here. As you see, maybe I can go with this animation. As we see here, we have two layers. The first one is a material, and then the second one is a different one. If the ray starts very specular, as we see on the left, then it would hit the specular material, and it would be still specular. So you see that lobe, that is the range of the light that would bounce us back. So that if it's wide, then it's very rough, as we see in the middle. So the specular light hits the second layer, and then it gets a bit rougher because of the scattering, and then it bounces back. For the last one on right, we see that the reflection, the transmission was already diffused. When we see a disk or a circle, that means always Lambertian function, which is widely diffused, and then it hits the second surface. And then once it bounces back, it would be still diffused. We don't have diffuser than diffuse, so that's how we show for two layers. So then, if you think of these two layers only, we have three options for the first one. We have three options for the second one. So there are 9 possibilities for this simple setup. And then think of it as a 3-layer, 4-layer. So this table shows that we have reflection and reflection, or if we have reflection and specular, reflection, diffuse, and then what model should we pick up? And then for these 9 possibilities, we can use pre-processing or some fancy pre-stored materials. So then we can just use it directly. So if I want to have a metal, then I would just pick metal. I don't need to care what happens inside, right? Then we have 3 interactions here. We have 3 layers. So this one, for example, is one of the examples. And then we have, we can include alpha. We want to include multiple interactions. Yeah, when we have a multi-layer, we assume that light would interact with the surface only once. If you want the surface to interact with the light more than once, they would be very expensive. So instead, you can add more layers instead, but still it would be under control. Again, everything here, the bottom line is to have everything under control while it's flexible. So we don't want to go crazy, because we don't need to know what is happening inside a medium or inside underneath a surface. We just care about what comes out. So we really don't need to know what is exactly doing with the physics. Whatever looks good, we're good. So that's the lesson of today. Then this one is another fancy shot from Wally, as we see the transmission, the lights, this kind of foggy subscattering, smooth appearance. And here we see the robot on right has reflection and subscattering, which makes it a smooth and a bit of translucency to it. And then here is that we have the leaves. They have, they show quite reflected when you see them from the front, because that's the front side of the model. And then if you go back from the behind the leaves, then you see that subscattering lobes pops up, because then it would be darker, as we know in real life, although it's not doing what light does, because that's very expensive, but still it feels correct. Then we have the ground here and then the water on it. So it's 2 different layers and how they interact with each other. So the results of this model, they were very happy with it because they have the flexibility. They have these 2 shows coming up, Wally and Up at a time. So it was a nice time to have a model that can cover all these materials. Fixed number of interactions with the light independence of layers. As we said, we don't want to go crazy with every layer. We need to have the light path under the control. Fixed amount of data per interaction. Pattern generation time could go up. Easier to factor shaders into layers than to build up complicated individual layers. Then they have it on GPU, so it's kind of independent. Every ray can go on one thread, so it really doesn't matter if it's on a GPU. It just goes faster. Lighters rarely had to touch the shaders. That's also an interesting point because they keep track of the amount of editing for every shot. And they realized after this new model, the shaders needed to edit what they want quite less frequent than what they had before. And that's a good point of the model because it means that with the parameters that are intuitive to tweak, you can get what you want right away. So then the speaker was saying that if I want to redo this, what would I change and what would I not change? So what they were planning to change is the choice of the lobe. So they to sample it based on the Monte Carlo, better sampling or whatever, deep into details. Then we have this distinguish between specular and reflection, which I guess it already happened because I don't think people do that now. Then we have early partial evaluation of view direction. View independent baking is very useful for stand-ins. Yeah, clear. Then what we don't want to change is the process itself. First point is to work with the users. That's very important to me as well. If you know what are your end users, so you're developing something, you're researching on something. If you know who are gonna be benefited from what you are doing, you will be more clear on your path and you can go directly to what you want. The second is the energy conservation. As I said, it's very important, otherwise you would get funky results. And the third one is the same visual phenomena important, possibly add retroreflection. So whatever happens inside the medium, we want to put that into account as well, instead of this diffuse approximation that we use. Still flexibility, we always want that. Even more important to minimize number of lobes. So now we have 3, can we do less? I mean, we have 3 on reflection, we have 3 on transmission. Can we go less? And thanks to these guys, and by the way, the last guy, John Warren, was my manager when I worked at Pixar. And the others are also familiar from research group as well. But to me, it's very interesting that this was 100% developed by Pixar, but it's always known as Disney, BRDF, which is weird. Yeah, that was my presentation. I'm gonna stop sharing my screen. And now if anyone has questions,